Hey everyone, and welcome to This Explainer. Today we are going to unpack the wildly fascinating culinary history and the physical science behind the world's absolute favorite frozen treats. Look, we all know the joy of grabbing a cold scoop on a hot day, right? But there is actually so much more going on beneath the surface of that dessert bowl. We're diving into a compendium of frozen confections, looking closely at how distinct ingredients, varying temperatures, and even just the simple addition of ambient air can literally rewrite the mechanical structure and flavor profiles of the desserts we love so much.
Here is how we're going to break it all down today. 1. The classic Big Three. 2. Gelato and its dense Italian tradition. 3. Frozen custard, the luxurious upgrade. And 4. Soft serve, which is fast and airy.
All right, let's jump straight into Section 1, the classic Big Three, exploring vanilla, chocolate, and strawberry.
Our palate for frozen confections evolved over centuries, and it was heavily dictated by when specific ingredients actually became widely available, as well as how early culinary pioneers managed temperature. Centuries ago, vanilla was already established as one of the most valuable flavorings in the entire world. We're talking about a prized, highly sought-after ingredient long before modern refrigeration even existed. Then, moving into the 19th century, chocolate ice cream really steps into the spotlight. This aligns perfectly with chocolate itself becoming commercially accessible and just generally easier to process into a smooth base. And jumping slightly forward into the early 20th century, we see frozen custard booming in the United States, utilizing dairy science in a totally new way. So, that modern dessert counter we all know and love, it's truly the result of centuries of steady culinary evolution.
And that history brings us to the present-day contrast between our two biggest heavyweights, vanilla and chocolate. Vanilla ice cream's superpower is its absolute versatility. Its sweet, clean, and incredibly smooth aromatic profile makes it the ultimate companion to almost any other dessert. It acts as this perfect base that just doesn't overpower other flavors. Chocolate, on the other hand, is a completely different chemical experience. By combining the creamy, fatty texture of frozen dairy with the rich, complex depth of cocoa, it actively balances its inherent sweetness with a slight roasted bitterness. This very specific ratio of fat, sugar, and cocoa solids allows it to stand boldly on its own, giving you a much heavier, distinctive sensory experience.
Rounding out the classic trio is strawberry. Now, this flavor is historically fascinating because its popularity historically spiked in direct correlation with the summer months, right when the fresh fruit was naturally abundant. Made simply with real strawberries, cream, milk, and sugar, it naturally takes on that iconic, beautiful light pink hue. But the real magic here? It's the volatile compounds that create its fresh aroma. The combination of sweet cream and the acidity of real fruit gives us a much lighter, fresher alternative to the heavier, richer dairy bases like chocolate. It perfectly captures that bright, acidic essence of summer in a single scoop.
Okay, so those classics effectively cover the foundational taste profiles we've all grown up with. But that leads us to a really crucial question that shifts our narrative entirely. What happens when you change the temperature and the air? This is exactly where the culinary arts meet rigorous physical science. What actually happens to the structural integrity and the flavor delivery of our desserts when we deliberately start manipulating these invisible physical properties?
Let's explore that in Section 2, Gelato, dense Italian tradition.
We can decode the exact science of gelato through a few key physical characteristics. First off, it actually contains less butterfat than many standard commercial ice creams. But the real structural secret? That lies in the kinetic movement during freezing. Gelato is churned at a significantly slower rate than standard ice cream. This slower mechanical process naturally prevents excess ambient air, which the industry refers to as overrun, from being whipped into the mixture. By severely restricting that extra air and keeping the overall fat content lower, the final result is a remarkably dense, heavy, and just incredibly smooth physical profile. It's literally a masterclass in how adjusting a simple mechanical process yields a vastly different physical texture. A crucial factor in this sensory experience is the serving temperature. Gelato is traditionally held and served slightly warmer than regular ice cream. So why does this thermal difference matter so much? Well, biologically speaking, extreme cold actually numbs your taste receptors. When a dessert is served at a deep freeze, your palate struggles to instantly detect the nuance of the ingredients. By serving gelato just a few degrees warmer, it completely prevents that numbing effect on your tongue. This warmer state allows those dense, heavily concentrated flavors to rapidly melt and stand out much more clearly on the palate. It's as if the temperature itself acts as an active, vital ingredient in the flavor delivery system.
Moving right along to Section 3, frozen custard, the luxurious upgrade. The fundamental difference you need to remember here is the chemical composition of the base. Frozen custard is extremely similar to traditional ice cream, but it is entirely differentiated by the deliberate inclusion of egg yolks in the base mixture. I know, it sounds like a minor, almost trivial tweak, but introducing that specific protein and fat alters the entire molecular structure of the dessert. We aren't just adding flavor here, we are completely changing the chemistry of how the water, sugars, and dairy fats bind together during the freezing process.
That one simple ingredient addition acts as a total mechanical upgrade. Because of the distinct fat content and the natural emulsifying properties inherent in the egg yolk, the standard ice cream base is completely transformed. The egg yolk forces the fat and water molecules to bond together far more tightly than they normally would. This creates a noticeably richer texture and a consistency that is undeniably smoother, creamier, and just incredibly stable. It basically takes a standard dairy dessert and chemically engineers it into a highly luxurious eating experience that coats the palate beautifully.
And finally, Section 4, Soft Serve, fast and airy.
Unlike the extremely dense, low-air gelato we analyzed earlier, soft serve goes in the complete opposite physical direction. It contains significantly more air than traditional ice cream. In fact, sometimes an enormous percentage of its total volume is just pure air. It's also served at a slightly warmer temperature to maintain its pliability. By mechanically pumping these incredibly high volumes of air directly into the base mixture as it freezes, you get that phenomenally light, fluffy texture. This high aeration also provides the precise structural stability needed to hold that signature, gravity-defying swirl shape we all instantly recognize.
Because it's so wonderfully soft and highly aerated, it's incredibly easy to push and dispense straight from a pressurized machine. You completely eliminate the need for the heavy physical labor required to scoop dense, rock-hard ice cream out of a deep frozen tub. This distinct mechanical advantage perfectly explains why it became an absolute staple of fast food restaurants, high-volume cafeterias, and roadside stands worldwide. It can be portioned and served in mere seconds and enjoyed immediately without waiting for it to temper. It is the ultimate dessert of convenience, driven entirely by manipulating its high air content. Comparing these varieties side by side reveals a genuinely fascinating inverse relationship between air content, serving temperature, and the resulting density. Traditional ice cream sits right in the middle. It requires a much colder temperature to maintain its structure, utilizing a standard air content. But gelato and soft serve are both served noticeably warmer, yet they possess totally opposite physical textures. The sole differentiator is the volume of air. Gelato purposefully uses less air, forcing the mixture to become remarkably dense and smooth. Soft serve deliberately pumps in maximum air, rendering it exceptionally light and soft. It's pretty amazing how simply manipulating the invisible metrics of air and temperature yields completely distinct dessert categories from very similar base ingredients.
As we wrap up this explainer, I'll leave you with this provocative thought to ponder. How will the invisible ingredients of temperature and air manipulate the flavor of your next frozen dessert? The next time you find yourself standing at a dessert counter, trying to mathematically choose between a dense Italian scoop, a rich emulsified custard, or a highly aerated swirl, you'll know exactly the underlying physical science of what makes each one so deliciously unique. Keep exploring, keep questioning the mechanics of what you eat, and I'll catch you in the next one.